ABC Listen. Podcasts, radio, news, music and more.
Hello, I'm JenniferLeake. On this RearVision, jet streams, how they were discovered, their crucial role in creating weather across the globe, and what can happen when they start behaving weirdly.
Getting caught in that jet stream was something any pilot would never forget. That wind was so strong. Our navigators and the bombardiers, they couldn't hardly sight anything where they were supposed to drop a bomb.
Pretty much every extreme weather event that you can think of is because the jet stream was doing something unusual. If you were to look at today's jet stream, you'd see that there are places where the winds are blowing quite hard, and there are places where you can't even find it. And there are places where it's even swirling, like if you sometimes go down a river, you find that there are eddies in the flow sometimes where it's just swirling off on its own. So you'd see all those sorts of things in the atmospheric jet stream, just like you'd see in a river.
Because the jet stream therefore moved much further north than normal, it changed the entire weather pattern across tropical Australia. Now, of course, in June, it's the middle of the dry season and rarely do we see significant rainfall, but this led to a rain event across tropical Australia that lasted more than a week.
Jet streams are narrow bands of strong wind in the upper atmosphere, and they can get really fast, up to 400 k's an hour. And because airplanes fly where the jet stream is located, they can have a big impact on flight times. How and why they form is a bit more complicated and can get quite technical, but this is a good overview.
There are jet streams in both the northern hemisphere and the southern hemisphere. Sometimes there's only one, and we would call that the polar jet stream. And sometimes there are two. So sometimes there's the polar jet stream and what we call the subtropical jet stream. And the reason there's a jet stream at all is because the polar areas are colder than the tropical areas. And that temperature difference between the poles and the areas closer to the equator, that is what creates the winds of the jet stream. And the bigger that temperature difference is, the stronger the winds of the jet stream are. It is not a straight river of wind. It tends to take these undulations north and south. So if you were looking at today's jet stream, you'd see that there were a number of these waves where it swings northward and southward. And those waves in the jet stream are associated with the weather systems that you would see on a weather map on TV. So things like high pressure areas and low pressure areas and fronts and things like that. So the jet stream is really responsible for creating those weather systems that affect our day-to-day weather.
What's slightly more complicated to understand is why you have such strong winds at 10 kilometres above the ground. And it's to do with the fact that you have warmer air over the equator and colder air over the poles. Now, cold air is denser than warmer air. And as a result, the height of the troposphere, which is where all the weather occurs, is lower in the poles and higher across the equator. Now, that leads to a very sharp pressure gradient. So if you look at your daily weather map on the nightly news, you've got your pressure gradient, and the closer the isobars, the stronger the winds. Well, if you looked at the pressure gradient 10 kilometres aloft, you'll notice that there are numerous isobars and they are packed closely together. There is a much tighter pressure gradient at the top of the troposphere, and that's why the winds are so strong.
The jet stream gets its name from what pilots observed during World War II in Europe and across the Pacific. The B-29 bomber was used by the United States in their aerial campaign against Japan. With pressurised cabins, the planes could fly at 30,000 feet, high enough so Japanese fighter pilots couldn't reach them. But the B-29 pilots encountered an unexpected problem when trying to reach targets in Japan. Extreme winds, which made accurate bombing impossible.
It was just a jolt to the experiences of these pilots. And when they came back and talked to the meteorologists at the islands where the planes were housed, they said, are you drinking or what? We don't believe you.
Yeah.
But then they started to look at the data a little closer and they said, I think maybe you're right.
John Lewis is a research scientist at the National Severe Storms Lab in the United States.
I got to know one of the pilots of the B-29 that went to Japan to drop the bombs, and he told me about his experience of being caught in the jet stream. And that is when another very large increment of knowledge came to me, because he told me about especially one trip where he had to go from Kyoto to Tokyo. That's about 200 miles. And he said we ran into 140 mile an hour wind. He said that was an approximation after we got back to land and looked at the data. But that wind was so strong, our navigators and the bombardiers, they couldn't hardly sight anything where they were supposed to drop a bomb because the plane was just all over the sky and nothing could be put into a state where you could make a good observation. But he said that was unbelievably, and this was an experienced pilot. Getting caught in that jet stream was something any pilot would never forget.
German meteorologists also had knowledge of this fast-flowing jet stream from their pilots in World War II. But these winds had been observed decades before by a Japanese meteorologist called Wasaburo Oshii. The paper he presented to international colleagues in the 1920s was ignored and overlooked for decades until John Lewis uncovered his work.
And after reading those papers, I said, here is the man who discovered the jet stream. I was trained by a Japanese scientist, and I really became appreciative of the Japanese culture and all that they had contributed, not only to meteorology, but to physics, chemistry, and whatever. But I really wanted to know if there was anything that happened in Japan that was related to the jet stream. Well, the professors and big academic people didn't know very much. That's what I came away with. But one of them, who I'd been communicating with for about 20 years, he said, John, he said, I do believe that Wasaburo Oshii had a lot to do with the discovery of the jet stream. I said, Wasaburo Oshii. I said, that name doesn't ring a bell with me. Well, it probably wouldn't, because he was a very practical meteorologist who worked for the Japanese Meteorological Society. And I do believe, from what I know, this was a Japanese man, that there might be some information probably in Japanese about him. And the good thing is, a lot of the information he sent me was not in Japanese, but was in Esperanto. This man he was talking about, Wasaburo Oshii, was an expert in Esperanto. So Esperanto isn't such a hard language to understand. It's a little bit like Spanish, it's a little bit like French, it's a little bit like German, a little bit like Italian. With a little bit of work, you can read Esperanto pretty well. I got these papers from Wasaburo Oshii, written in the 1920s in Esperanto. And I said, oh my golly, I found a chunk of gold. I found a chunk of gold.
So why was a Japanese man compelled to learn Esperanto? We're going to take a short detour. Emeritus Professor Rolly Sussex is a linguist at the University of Queensland. When did Esperanto first emerge? What's the origin story?
We've got a date on that one, 1887, and it was the invention of a Polish ophthalmologist in Warsaw called Zamenhof. He grew up in a Jewish family, and his first languages included Polish and Yiddish and Russian. Being Jewish, he also learned Hebrew and knew some Latin and Greek as well. He was quite a goer. And in his area of eastern Poland, which was then Western Russia, the Russians actually forbade the use of Polish language in public. And he was intensely aware of the sensitivity of language. And the word Esperanto actually comes from the verb to hope. Oh. It's espérer in French and esperar in Spanish and in Portuguese. And it is a hopeful language. The idea was that we would have something which people would use for clear interpersonal communication. It would be easy and transparent, and it would not have any of the historical values that had become associated with the Russians and so on. He published a dictionary in 1894. Okay. Because, once you've got a dictionary, a list of words that you can use, and Esperanto did okay. It's known worldwide. There are packets of Esperantists in South America, in parts of Asia, particularly Japan, interestingly.
If there was a bit of hope and, people were getting behind it, what do you think stopped the growth of Esperanto? Why perhaps it, faded away?
The fact that until 1919, French was the language of international communication, particularly in Europe. Anyone who was educated at all learned French. Mm. The interesting thing there was that the first international treaty, which was not in French, was the Treaty of Versailles at the end of the First World War in 1919, which was in English and French. And from that moment, French starts to decline and English takes off.
Why do you reckon Japan really got into Esperanto?
I think it was because of the attraction of something which was above the existing languages, something which was transnational and independent and had none of the baggage which the other languages brought with them. And so I think the notion that here was something which people could communicate in, which was not English or French or one of the other big languages, but was something which was independent and fresh.
In the 1920s, Wasaburo founded and was appointed director of the Japanese Aerological Observatory. And this is where he started his experiments, releasing hundreds of research balloons near Mount Fuji, and by tracking their position, he was able to determine the wind speed. Between 1923 and 1925, he made almost 1,300 observations of high-altitude winds.
The word jet stream was not in the language. He just discovered this very strong current of air in the upper levels of the atmosphere from anywhere from, I'd say, 18,000 feet to 30,000 feet. And he went to the Aerological Commission where he met with these other scientists, probably about 30 scientists from around the world. And he brought his information in Esperanto. I have the document that he brought to that meeting, and I would say almost universally it was ignored. It was ignored. And I said, oh my goodness, the people who were involved in these upper air business didn't realize what a piece of gold this man brought. But you have to remember, at Japan at that time, the early 1920s, they were not respected in science at all, hardly at all.
But by the 1930s, the Japanese military took over the upper air observatory he directed, taking control of all of his data. And they weren't interested in Wasaburo doing any further research. Instead, they used his information to help launch Operation Fugo.
They launched 9,000 balloon bombs from Tokyo, and 300 of them got to Canada and the United States. So about 3% of the balloon bombs they launched got to the destination, which unfortunately did kill several people. They used Wasaburo's data and his knowledge of the wintertime winds, because they would want to launch those balloon bombs when the winds were very, very strong, because even under the strongest winds, it would take 3 to 4 days for the balloon bomb to reach Canada or the United States. His data was used for military purposes, and I'm sure that just saddened him to no end. I don't know him personally. I didn't know anybody who knew him personally, but I would just say, knowing a little bit about his past and the way the military took over, he was probably very saddened by how his data was used.
And one of the reasons these balloons didn't reach their targets, we still didn't know about the meandering nature of the jet stream. And Wasaburo's observations only applied to localised winds over Tokyo. It wasn't until the 1950s that we began to understand that these fast-moving highways in the upper atmosphere travel all around both hemispheres. This is RearVision. I'm JenniferLeake. Predicting the impact of global warming on the jet stream is at the frontier of climate science.
In the Northern Hemisphere, one of the big impacts on changes in the jet stream is the fact that the Arctic is warming 4 times faster than the globe as a whole. It means that north-south temperature difference is getting smaller. And when we see that temperature difference get smaller, the winds of the jet stream generally weaken. And we know that when the jet stream is weaker, it tends to be more easily deflected from its west to east path by mountain ranges, blobs of ocean temperature that are either warmer or colder than normal. That tends to create the conditions that lead to these big north-south swings in the jet stream. So these bigger waves, if you will. And when those big waves are in place, we tend to see them sticking around a long time. So big waves move slowly, small waves move faster, and the weather systems that those waves create also move slower and faster.
Jennifer Francis is a senior scientist at the Woodwell Climate Research Centre.
It's not just about the Arctic warming so fast. We're seeing the oceans generally warming, and certain areas we're seeing oceanic heat waves becoming very persistent and very expansive. So right now there's a very intense one off of the UK and Spain. You might have heard in the headlines where the temperatures there are running 8 even more degrees Celsius warmer than normal, which is an incredibly huge temperature aberration for an ocean. Anything that changes temperature patterns is going to have an influence on the jet stream because winds are created by temperature differences, horizontal temperature differences. So anything that affects those temperatures is also going to affect the jet stream. We have some understanding of how weather patterns are affected by the different phases of El Nino or La Nina, but there are all these other factors in place now that we've never seen working at the same time. So El Nino is happening in a situation with all these oceanic heat waves with a very warm Arctic. And so we don't really know what's going to happen as this El Nino comes along. And it's looking like it's going to be a very strong one.
There's a lot of uncertainty around how rising global temperatures are impacting the jet stream. Research is ongoing and more sophisticated climate modelling is needed. But changes in the jet stream are steering autumn rain away from southeast Australia.
Well, I'm visiting fellow at the School of Mathematical and Physical Sciences, University of Technology.
And why don't you reference that you're also speaking to me from a campground in Denmark, because I love that as well. I can hear the birds. I like that.
Okay, I'm speaking to you, Jennifer, on the island of Funen, and it's been such a wonderful experience riding around Denmark on a bicycle. The subtropical jet and the polar jet have shifted poleward by up to about 5 degrees latitude. And so as a consequence, for example, systems like East Coast lows are forming further south and further east, actually, away from the coast.
And what's the impact of those weather systems you just described? How does that potentially show up in the kind of weather we're getting?
One example is May, just gone in 2023, was one of the driest Mays we've had on for quite a while. But, I mean, that's been happening for the last 10 or 20 years in southeastern Australia, particularly over inland southeastern Australia.
We're speaking in late June, in winter. Tom Saunders is a meteorologist with ABC News. What are we seeing with the jet stream, the subtropical jet in parts of Australia at the moment?
So late June 2023, a very interesting situation occurred where some cold polar air moved all the way up through Western Australia, even into the central parts of the Northern Territory. Now, because that cold air moved much further north than normal, it displaced the subtropical jet. Now, remembering a jet stream is the boundary between colder air and warmer air. So because the jet stream therefore moved much further north than normal, it changed the entire weather pattern across tropical Australia. Now, of course, in June, it's the middle of the dry season and rarely do we see significant rainfall, but this led to a rain event across tropical Australia that lasted more than a week. And we saw heavy rain and even some areas of flooding across the north. So it had a massive impact on the weather through the northern half of the country.
We can talk about the subtropical jet having a kink in it. What made this particular example a little bit weirder than usual?
Generally, the subtropical jet stream runs from west to east, and it has very sort of small, shallow waves in it. The polar jet stream, on the other hand, often has quite amplified waves, but on this occasion, the subtropical jet stream had an amplified wave. So moving in from the Indian Ocean across Western Australia, it then surged north, so a massive bend or kink in it, right across even into the northern part of the Northern Territory. So that was quite unusual to see such an amplified wave, and it did last for around a week as well, which is what led to the longevity of the unseasonable rain.
Commercial use of the jet stream began in the early 1950s when a plane flew from Tokyo to Hawaii, cutting the trip time by over a third. And occasionally planes get an extra boost within the jet stream. It's called a jet streak. Matthew Capucci is a meteorologist.
So let's say you're an airplane, for example. You might be traveling at 800 kilometers per hour airspeed. But what if the air around you is also moving at 300, 400 kilometers per hour, as is the case in a jet stream? So if these two are working together, if you're being blown in the same way that you're already flying, you kind of team up and you can have speeds 1,100, 1,200 kilometers per hour for a commercial aircraft. And that was the case with this plane that flew into the jet stream with the jet stream. You sometimes have little extra narrow sort of bursts of the jet stream where the winds are even funneled a little bit faster and faster, called jet streaks. So if you have an aircraft that flies with a jet streak in the right direction, you can really have impressive speeds.
Jet streams can make your flight quicker or longer. They can also make your flight bumpier. You've just flown in to LA, is that right?
Yeah, that's correct. So landed in LA about an hour and a half ago and just made it to the hotel. My name is Steve Cornell and I'm the Safety and Technical Director at the Australian and International Pilots Association and a first officer on the A330 with an Australian-based airline. So we do get forecasts around where there may be areas of clear air turbulence, but it's a bit of an inexact science. So, I mean, fortunately, you're rarely the first aircraft, going across to Perth or going across to Sydney. There's usually traffic in front of you. And if there is clear air turbulence, it's likely that those other aircraft have experienced it as well. We have a system where we make reports when we encounter that turbulence, so that can be passed on to the benefit of other traffic. If we know that there is clear air turbulence around, then we can do things like, change altitude or turn the seatbelt signs on and have everyone seated until we get through that area. If we're unlucky enough to be the first aircraft to come across it, then it's just a matter of securing any loose items in the cabin and turning the seatbelt signs on, possibly reducing speed just to smooth out those bumps. And then probably the most common response will be to try and find a smoother altitude, because the jet stream itself, while it's very long, is not usually very deep. And, if we change altitude by just a few thousand feet, we're usually able to find some smoother air.
And clear air turbulence in the jet stream is increasing. Professor Paul Williams is an atmospheric scientist at the University of Reading.
Very recently, we've published a study that shows that actually these increases have already begun because, of course, humans have been changing the climate for over a century now. And so it stands to reason that the turbulence should already have started to increase. And indeed, we have evidence now that it has. There's 55% more severe clear air turbulence over the North Atlantic today than 40 years ago, 41% more over the US, and similar figures elsewhere around the world. So these projected increases that we have been floating around for many years now actually have already started to happen. I mean, as you know, if you drive your car over lots of potholes, it's going to need to be serviced more, and sooner or later the suspension is going to break. And it's much the same with aircraft flying through turbulence. More turbulence means more fatigue on the airframe. Airbus, Boeing, etc., who are today designing the planes that will be flying in the air in a few decades' time, when there could be twice or three times as much turbulence. They're very keen, understandably so, to make sure that their design specifications result in planes that are fit for flying through all that extra turbulence. And so I'm working closely with them to try to achieve that.
What are some of the more dire predictions that your work is showing us in terms of how much more clear air turbulence we could see, even just in the next 10 years?
Well, we know that climate change is changing the jet stream. The jet stream is 15% more strongly sheared today than it was 4 decades ago. We know that from satellite observations. And the projections are that as we continue to warm the climate, it will become even more sheared. And our projections indicate a doubling or a trebling in the amount of severe turbulence. Usually the future reference period is 2050 to 2080, so a few decades into the future. The up and down motions of the plane in severe turbulence will be stronger than gravity, and so if you're not seatbelted, you will lift up out of your seat in severe turbulence. So it does have the potential to injure people.
There's something else John Lewis did with the data from Japanese meteorologist Wasaburo Oishi. He compared his observations from the 1920s with what we know today.
And I said, I want to compare what he had for these wintertime averages of winds over Tokyo with what we know now. So I then went to Japan, and not personally, I talked to them, but I got all their observations for the wintertime in recent years. And I then calculated the direction and speed of the wind from the surface up to about 30,000 feet. And then I compared it with that figure from 1926, and they almost overlap perfectly. Wow. So the latest observations validated what this man did with primitive equipment. I couldn't work for a few days. I was so emotional. Just admired this man so much.
John Lewis is a research meteorologist with the National Severe Storms Lab. Thanks also to Jennifer Francis, a senior scientist at the Woodwell Climate Research Centre. Professor Paul Williams is an atmospheric scientist at the University of Reading. Also in the program, meteorologist Matthew Capucci. Milton Spear is from the University of Sydney. Steve Cornell is a commercial pilot, and Tom Saunders is a meteorologist with the ABC. This Rear Vision was produced by me, JenniferLeake, and sound engineer Anne-Marie de Bettencourt for ABC RN.
You've been listening to an ABC podcast. You can discover more ABC podcasts, live radio and exclusives on the ABC Listen app.